Good morning. I'm Arturo Muñoz, and I want to present you our method to model and analyze large floating wind turbines. It is based on vortex-lattice aerodynamics and on nonlinear structural dynamics. I work with Rafael Palacios and Andrew Wynne at Imperial College London, and I am ESR 11. So wind turbines are becoming very large to increase the power capture, and they are becoming very flexible to reduce the cost. And moreover, they are being operated in complex inflows because of the terrain or because of the influence of other wind turbines. The simulation of these systems is becoming very difficult, especially when they are placed on floating structures. The testing of this system is also very expensive because of the size of the components and the whole system, and because of the difficult scaling of this system because of the different physics involved. So then computational methods offer an efficient and accurate method for the wind turbine design, and that's what we are going to work on. Our objective is working with low and medium fidelity methods for the wind turbines, and as a first objective, propose improvements for them. So this way, we are trying to increase the accuracy or reduce the computational cost of these methods. We are also going to analyze how these methods perform in traditional inflows for wind turbines, as the uniform steady inflow, the yaw, and the turbulent cases. And finally, we are going to investigate how the elasticity of the system and the floating dynamics of the system influence the power production and the system loads. These are the three methods that we are going to talk about today. We have blade element momentum, or BEM, which is very accurate in steady uniform inflow because all the hypotheses of the model are fulfilled in this case, and because it has also been tuned throughout decades to be accurate in this situation. It is an extremely efficient method, but it needs corrections when it comes to complex inflows like the yaw case or the turbulence case. The yaw corrections have been proposed many years ago in literature, and we will see how they work in this presentation. And I will also show you a correction we have proposed for the turbulence cases. The second method is an steady vortex lattice method. Mark has just talked about it, UVLM. For us, the important part is that it accounts for complex aerodynamics, like the three-dimensional and the unsteady effects, which are not accounted for by blade element momentum. It is more computationally expensive, and the main drawback is that it does not account for viscous drag, but we have proposed in this presentation a method to account for it. And finally, we have LES with actuator line, or large eddy simulation with actuator line, which is very convenient to model wakes and the interaction between wind turbines, but it is extremely expensive computationally. So I would like to start presenting you a method we propose to reduce the cost of UVLM. So in this figure, you can see the UVLM mesh for solid surfaces in dark gray, and in light gray, you can see the wake. The wake is just a two-dimensional surface that where the vorticity of the flow is contained. Okay, so this wake surface is going to move together with the flow according to equation 1. So in an inertial frame of reference, the movement of this surface is very simple. Every closed curve partial sigma in the figure is going to move according to equation 1, and it will retain its vorticity, or equivalent the circulation along that curve, due to Helmholtz theorem. However, in aerodynamics, we usually use non-inertial frame of references moving with solid surfaces because the influence of the vorticity on the solid surfaces decays as 1 over the distance between the two. And this establishes an effective convection according to equation 2 that you can see there of the circulation of the of the flow. If we perform a first order upwind discretization of this equation, we get to equation 3, in which we can see the C coefficient, which is also known as CFL coefficient. Traditionally, UVLM generates grids that comply with C equal to 1, because it makes the numerical treatment of the system extremely simple. As you can see in equation 4, the only thing that we do at every time step is shift the circulation from one panel to the next one. However, this constraint forces us to have a uniform discretization throughout the wake. In these pictures, you can see the upper view of an airfoil in gray and the wake colored with the flow circulation. And as you can see on the left-hand side, if we discretize the whole wake with a constant panel size, the computational cost increases massively, because the computational cost of UVLM grows with the number of wake panels squared. So what we propose is to go for a discretization like the one on the right-hand side, in which we coarsen the panels as we get away from the airfoil. It is important to point out that this does not come at the cost of reducing the accuracy, because we are coarsening the panels very far away from the airfoil. And for example, in this example that I'm showing, as far as we mesh fine enough just one chord of the airfoil behind it, we get accurate results. However, to capture, for example, the tip effects, we need a wake that is of the order of 200 chords. So the reduction of the number of panels and thus the computational cost is huge. There is a practical issue that we need to overcome when we are using wakes with this kind of discretization. In these figures, you can see an airfoil in black and the wake in light gray. At every time step, the airfoil will move forward and the wake will be convected downwards. And we will need to generate a new vortex in the space generated between those two. You can see the new vortex there. And thus, for computational efficiency and convenience, we would need to remove one vortex as well to keep the number of vortices constant. And that will imply removing vortex 4 star. If we do this in a non-uniform discretization, we will end up with a very short wake at the end of, I don't know, maybe 100 time steps. And that will reduce the accuracy of our computations a lot. So what we need to do after every time step is a step of mesh regularization or remesh the wake that we have. For the cases of airfoils with flat wakes, we can just do linear interpolation in Cartesian coordinates, and this is very simple and works very well. However, for wind turbines that they have helicoidal wakes, if we do linear interpolation in Cartesian coordinates, you can see in the scheme what happens. And what happens is that we get a radius reduction of the wake that is not acceptable if we want to have an accurate result. On the other two figures, you can see what happens in a simulation between time 0 and time 45. And the wake structure is completely destroyed just by the interpolation scheme. So what we need to do is to do linear interpolation in cylindrical coordinates, or use interpolation method called SLERP for this interpolation. And that solves the problem of the radius reduction. Next, I am going to show you the different inflows that we can find in wind turbines and how our models perform in each one of them. We are going to start with the uniform steady inflow, in which BEM is very accurate. So we are going to use it as a reference. And in this case, the loads are constant along the revolution. So what I'm showing here is on the upper row, you can see an indicator of the structural loads that the wind turbine or the blades suffer. And on the bottom row, you can see an indicator of the power production, both of them along the span. If we look at the left-hand side column, we can see the standard implementation of UVLM and BEM. You can see that the prediction of structural loads is very similar between both of them, but UVLM significantly overpredicts the power production. And this is because UVLM does not account for viscous drag. So at this point, we thought, how does BEM account for viscous drag? And it turns out that the only thing that BEM does is getting the value from lookup tables. So we put the same lookup tables in UVLM, and if we use that model, you can see on the right-hand side of the figure that we get a very good agreement in both the structural loads and the power production. The second flow, or the second inflow I want to show you is when the wind, it is not parallel to the rotation axis of the wind turbine. In this case, we say that the wind turbine is operating in yaw, and very important and steady and three-dimensional effects appear. This complex aerodynamic phenomena is not accounted for by BEM, by the standard implementation of BEM that is shown here in dashed red line as BEM no skew. And as you can see, it fails in predicting the maximum and the minimum location of loads along the revolution, and also the amplitude of those fluctuations. There are literature models to account for these effects, which is the yellow line labeled as BEM skew, and those models improve a lot the results, both in the location of maximum and minimums, and also in the amplitude of the fluctuations. In these cases, the UVLM and the LES results are very accurate because they both account for these unsteady and three-dimensional effects. And the third flow we are going to see today is the turbulent inflow. When we have turbulent in the wind, okay? So on the left-hand side, you can see how we compute the lookup tables we were talking about before in blade element momentum theory. These lookup tables have the lift and drag forces as a function of the angle of attack. And the way we compute those tables is from wind tunnel experiments in wind, where we create a model that has constant cross-section, and thus it doesn't have any three-dimensional effect. What BEM does is when you go to the wind turbine blade that doesn't have constant cross-section, we just assume that the lift and drag forces from the angle of attack is going to be the same as the 2D lookup table that we got from wind tunnel experiments. If the properties change slowly along the span, this approximation is quite good. However, when we have turbulent flows, the relative velocity VR in the figure changes very quickly along the span, and then we have three-dimensional effect, and the previous assumption is not valid anymore. Let's see what UVLM does with these cases. Here you have the blade mesh with UVLM. You see that we mesh the span-wise direction. We also mesh the chord-wise direction. And UVLM inherently accounts for these three-dimensional effects. We are going to focus on lift because we have already said that the drag in UVLM is not good enough to use it. And UVLM is more expensive than BEM, but our idea is we are going to study this span-wise variant flow with UVLM and see if we can apply it to BEM somehow. So we set up this case in which we have an airfoil with constant cross-section, and we subjected it to an inflow that is steady and that has a sinusoidal shape in the span-wise direction, as you can see in the figure on the left. On the right, you can see the lift force coefficient along the span for both the 2D approximation and the 3D approximations. As you can see, the average value is the same in both cases, but the three-dimensional approximation significantly reduce the peak-of-peak value of the signal. So what we did next is study this effect at different wavelengths of the input. So in these figures, you can see the relation between the peak-to-peak lift coefficient. We plotted the ratio between the 3D approximation and the 2D approximation. On the left-hand side, you can see that this relationship doesn't change with the initial angle of attack of the airfoil. And on the right-hand side, you can see that it doesn't change either with the amplitude of that sine signal that we have at the beginning. So what we did is we created a filter with this function, we call it HC, and we use it to filter the two-dimensional estimation of lift that BEM does. And we filter it with this filter such that we put the three-dimensional effects on that lift distribution. So here you can see again structural loads on top, power generation on the bottom. In this case, the left-hand side is just a snapshot of the simulation, so just one time step. And on the right-hand side, you can see the average loads along a revolution. There are three lines. The gray line is UVLM, which, as we have said, accounts for three-dimensional effects, so is what we use as a reference in this case. The dotted black line is the standard BEM implementation. As you can see, especially on the left column, shows very significant fluctuations along the span. It also shows fluctuations on the right-hand side column, but obviously as this happens throughout a revolution, the fluctuations are averaged out. However, if we apply the filter that we have just created to the blade element momentum theory, which is the red dashed line, we see that our prediction of the loads is much closer than UVLM, both at every time instant and when we average the loads along the revolution. So that was about rotor aerodynamics, but now we want to study how the floating dynamics influence this physics. Okay, so we have created a very basic model for the floating dynamics, in which we have quasi-steady mooring. Mooring lines are the lines that hold the wind turbine in place. This model does not account for dynamic effects or drag, but it is very convenient to get the mooring forces from the position and orientation of the platform. Then we have a linearization around the equilibrium position of the hydrostatic forces. And for the hydrodynamics, we are going to use, again, potential theory. We are going to solve the radiation problem, which is the waves generated by the structure when it moves at a certain frequency. And this is done with the added mass and the damping matrices of the system. And we also account for the diffraction problem, which is the forces that the structure has when there are waves. Finally, the only thing that this model doesn't account for is viscous drag. So we included this viscous drag as at every cross-section of the platform based on Morrison's equation from the drag coefficient and the relative velocity between the solid and the structure. We also include, well, the Aeroservoelastic solver that we have at Imperial College London already has the nonlinear beam dynamics, which are very convenient in our case because they account for nonlinearities due to large rotations. And they also account for the change in the aerodynamic surfaces once the structure has been deformed. We also put in this code multi-body dynamics based on Lagrange multipliers. And again, it's the same solver Mark was talking about, this SARPy. It's open source and you can find it on GitHub. So to validate the floating dynamics, we implemented the NREL 5 megawatts wind turbine with the OC3 floating platform. And we ran these cases to compare against the literature. These validation cases consist on displacing the wind turbine from the equilibrium position in one of the three directions or rotating it in one of the three main rotations and let the system evolve and see and record that evolution. In the left-hand side, we have displaced the wind turbine backwards, and we recording the backwards forward movement. And as you can see, we have good agreement with the literature results. And on the right-hand side figure, we tilted the wind turbine backwards, and then we let it evolve. And again, we have good results comparing with the literature. But in these cases, we not only have one main movement, we have coupling in our system, mainly due to the floating dynamics. And as you can, this image show again the case in which we tilt the wind turbine backwards and we let it evolve. But as you can see on the left-hand side, the wind turbine also moves up and down. And on the right-hand side, you can see how it moves backward and forward. These cases, these movements have smaller amplitudes than the main movement, but we still have good agreement with the literature results. So I would like to conclude saying again that unsteady and three-dimensional aerodynamics are very important for rotor aerodynamics. We have proposed some improvements for low and medium fidelity methods, such that we have increased their accuracy without increasing significantly the computational cost. We have reduced the computational cost of UVLM by the new wave convection equation discretization. We have included drag in UVLM following the BEM philosophy. And we have included three-dimensional effects in BEM based on a study performed with UVLM. And we are finishing now how the elasticity and the floating dynamics influence the behavior of our system. Here you have my conference papers and my journal papers. And the last, as I said yesterday, I'm currently writing up and finishing the last computations, hoping to submit by September the 13th. And in the future, I would like to keep working on wind energy, either industry or research, but I haven't thought about it. So I will wait until I submit my thesis. Thank you.